Hello, hello, hello. Hello, am I audible, Herschel? We will start the lecture in couple of minutes. So let's start today's lecture. Am I audible? Can you just confirm, Harshal? You can write in chat box. Okay. So in this session we are solving this previous year GATE questions. Earlier we had covered the subject of heat transfer, and now we have started on this process control subject. In the last lecture, that is a week before the previous week, we discussed the preliminaries of the subject and what this subject, that is process control and instrumentation, covers, what all concepts will be required, and then we started with these first order systems. So let's just revise that first order systems. So we derived this for equations related to first order system for a mercury thermometer. Okay, so the model equations or the dynamic equations governing the enthalpy balance of this mercury thermometer are will give rise to this first order systems. So just to revise, the differential equations or the model equations, whatever you want to call it, for this first order systems are in general of the form of tau dy by dt plus y is equal to kp x, and where x is a function of time. So here tau is the time constant. For any of this first order system, tau will always be the time constant. Kp is the process gain. Xt are my inputs, and y will be a function of time. Also, it can be a function of x also. So these are the outputs. Now our main purpose is to model this system mercury thermometer such that we get a relationship between input and output. So for that we need to solve this equation, and in this process control subject we typically use this Laplace transform of this equation to derive a transfer function of this system. So we use Laplace transform, so that will give us the transfer function of the system, that is ys upon xs. And for first order system we can remember the form as kp upon tau s plus 1. This is the general form of transfer function of first order system, and we denote this transfer function as capital G of s. So all these parameters are in s domain. Now to bring this system in time domain, so we need to provide the input. So let's just consider if the input that we are providing is a step input. So basically if we are having a constant value, and then at a time, let's say t equal to 0, we provide a step input, that is we change the input of the system and then keep it as constant. So this is known as step input, and the general formula of this step input is of the form of a by s. For here we are considering this unit step input, so we have written it as 1 upon s, and then we can replace this xs is equal to 1 upon s in here, and then we can get ys as some function of g of x into x of x, and then we can take the inverse Laplace of this equation to find the solution of this equation in time domain. So that is, we will be getting y of t is equal to kp 1 minus e raised to minus t upon tau. So this is the general solution of a first order system, where kp is the process gain, t is the time instant at which we need to find the value of yt, tau is the time constant, and yt yt, you need to remember yt is always y minus ys, that is how much deviation is occurring from the steady state. That is how we define this yt. I hope this much revision is sufficient from the last class. If you have doubts, then you can write it in chat box or just speak up. So in last class we looked onto this thermometer example that was from GATE 2012, question number 24. So in this question, we will just revise this question again. And in this question, we were given that the thermometer at 100 degrees Celsius is dipped at time t equal to 0 in oil bath and maintained at 150 degrees Celsius. If the recorded temperature is 130 degrees Celsius in 1 minute, then we have to calculate the time constant, that is tau. So if we draw this temperature relation with time, so initially the thermometer was at 100 degrees Celsius, and at time t equal to 0, we change the input, that is we increase the temperature of, we put the thermometer in an oil bath of temperature of 150 degrees Celsius. So this was 100 and over here it is 150 degrees Celsius. And since the temperature of oil bath has changed, the thermometer will measure this temperature, but it won't do it instantly. It will follow this trajectory of the first order system. So this first order system will follow such a path. And over here we have been given that at time t equal to 1 minute, that is somewhere over here, the temperature we have been given as 130 degrees Celsius, and we have been asked to find tau. So since this thermometer is a first order system, we can write the response corresponding to, this was the step input, as yt is equal to kp 1 minus e raised to minus t upon tau. Now yt is how much deviation is occurring from the steady state. So the steady state is 100, and we have to find the time at 1 minute. The recorded temperature is 30 degrees Celsius, so the deviation is 130 minus 100, that is equal to 30 is equal to kp. Kp is the process gain, that is from 100 we are changing the input to 150 degrees Celsius, so the process gain was 50. Time we have been given as 1 minute and upon tau. So we solve this equation, and corresponding to that we will be getting this time constant tau. So this was all we covered in the last class related to modeling of the first order system for thermometer, and then few of the characteristics of first order system, and then we looked into this example of step response corresponding to this example. So now let's look at the second question. So this question is from GATE 2014 chemical engineering paper, and question number 14. The question is, so assume that an ordinary mercury in glass thermometer follows first order dynamics with a time constant of 10 seconds. That is, we have been given time constant is 10 seconds. It is at a steady state temperature of 0 degrees Celsius, that is ys, we can write it as 0. At time t equal to 0, the thermometer is suddenly immersed in a constant temperature bath of 100 degrees Celsius. So if earlier the time was, let's say, 0, and that the temperature over here is 0, and at time t equal to 0 we are immersing the thermometer in a temperature bath of 100 degrees Celsius. So over here the temperature is 100 degrees Celsius, and the temperature measured by the thermometer will follow such a path corresponding to the first order system, and we have to find out how much time is required for the temperature to reach the temperature of 95 degrees Celsius. So over here the temperature is 95 degrees Celsius and we have to find the time taken. So I will share the video solution. If there are any issues related to audio, just let me know. This is a fairly simple question, similar to the questions that we discussed last time. Question number 14. Hello everyone. We are solving question 14 of GATE 2014 chemical engineering paper, and the subject related to the question is instrumentation and process control. And we have the question. I have just read the question, so I will skip the question reading part. Time constant T equal to 0, constant what at 100 degrees Celsius. The time required for the thermometer to reach 95 degrees Celsius. So let's consider the time taken by the thermometer to reach 95 degrees Celsius is T. Then at y of t, we have been given the temperature as 95 degrees Celsius. So we draw this kind of plot where this shows y or x. So initially, let's consider this as time equal to 0. At time t equal to 0, the temperature recorded by the thermometer is 0 degrees Celsius. So here it is 0 degrees Celsius. And then thermometer suddenly immersed in a constant temperature about 100 degrees Celsius. So you can say that now this is 100 degrees Celsius. Now the temperature recorded by the thermometer will follow this first order dynamics with time. Basically it will be like this. So these are my y, or the temperature recorded, and if this is 95 degrees Celsius, then we have to find time taken by the thermometer to reach 95 degrees Celsius. So in this case, we can see that the step input is given to the system of the magnitude A, and where A we can call it as 100 degrees Celsius. Step input of magnitude A is equal to 100. Now we know that thermometer follows the first order dynamics in the given question, and also, so by first order dynamics we mean that the transfer function would be the form, or the process model would be of the form of tau dy by dt plus y is equal to kp x of t, and for this transfer function we can write it as g of s is equal to y of s upon x of s is equal to kp tau s plus 1, and the x of s we have been given step input of magnitude 100, that is we can write it as 100. Transfer function corresponding to that will be 100 upon s, or 100 was a, so a upon s, and the output response in time domain will be y of t is equal to a 1 minus e raised to minus of t upon tau. We will be using this equation to find time required by the thermometer to read 95 degrees Celsius. So y of t is equal to a is 100 degrees Celsius, 1 minus e raised to minus t upon tau we have been given as 10 seconds, and this time we have to find. Now y of t is y at time t minus ys is equal to 100, 1 minus of e raised to minus t upon 100. Y at given time is 95 degrees Celsius, and at steady state the temperature was 0 degrees Celsius. So this is 10 seconds. So basically 1 minus e raised to minus t by 10 is equal to 5 upon 100 is equal to 0.05. We can write this as e raised to minus t upon 10 is equals to this e raised to minus t by 10 will be 1 minus of 0.95 is equal to 0.05. So we can take log of this equation and we will be getting minus t upon 10 is equal to ln of 0.05 is equal to minus of 2.995. Basically the time will be 29.95 seconds. So it will take around approximately 30 seconds for the thermometer to record a temperature of 95 degrees Celsius. So from the given options, we can select that the time required by the thermometer to reach 95 degrees Celsius is approximately 30 seconds. So this question was very similar to the previous question. In the earlier question, we were asked to find the time constant, and in this question, we were given the time constant and asked to find the time required by the thermometer to reach a certain temperature. Now let's look at the next question. So this is question number 10 from GATE 2014, and this is also related to first order system. The question is a unit impulse response of a first order system with time constant tau and steady state gain kp is given by dash. So in this question we are given this unit the input that we have been provided is the unit impulse response, and in the earlier cases we were considering step input, and for step input we had seen that the response is given by yt is equal to kp 1 minus e raised to minus t upon tau. So this is for step input. Similarly, in this question we have been asked to find if the input is impulse input, then what is yt that we have been asked to find. So let's just revise the three main types of inputs that can be provided. So the first one is impulse input, and in impulse input what we do is we increase the temperature, keep it for some time, and again decrease the temperature. So that is we are providing an impulse in the input or temperature in the input. So for this impulse response, if we want to write the transfer function that is of the input, that is input in S domain, that is we can write it xs is equal to xs is equal to a, we can write. And similarly for in time domain we can write it as x of t is equal to a times delta t, where this is the Dirac delta function. And this other kind of input that we will be dealing mostly with is step input. In step input we increase the temperature, increase the input to a fixed point and then keep it as constant, and the transfer or the equation in S domain will be xs is equal to a upon s. And if we want to write this a upon s in time domain, we can write it as x of t is equal to a times of unit step change, that is u of t, and where a is this step change. The third case we can write it as ramp input. So in ramp input we keep on increasing the input variable by a constant rate. So that is we can write that xt is equal to a times of this time, where a will be the slope of this curve. And if we take the Laplace transform of this function, then we will be getting x of s is equal to a upon s square. So in this question we have been given this impulse input and have been asked to find the corresponding y of s. So let's take a look on to the video solution of this question. This with time constant tau and process gain at steady state as Kp. So the model equation corresponding to first order system, you can write it as tau dy by dt plus y is equal to Kp into x, where x is a function of time, and corresponding to this, the transfer function by taking the Laplace of this equation, we can write it as g of s is equal to y of s on x of s is equal to Kp tau s plus 1, where x is the input that has been provided to the system and y's are the output or the values measured by the system. Now in this question we have been given a unit impulse input. So this is our xs. So by unit impulse input we mean to say that if this is x versus time, so by unit impulse input we mean to say that the input to the system is of this form, where this is a time, let's say 0 b, and the magnitude is, the area will be a, so this will be a upon b. So this is our impulse input. Similarly, if the step input, we can plot it as this is a t and the time t equal to 0. We are just giving a step input, that's basically increasing the magnitude by a value of a and keeping that at constant. So this is step input. So the kind of input that we can provide to a system is a ramp input, in which we keep on constantly increasing the input value x t, and the slope we can write it as b. So corresponding to this, let's say last one is ramp input. So corresponding to this impulse input, we can write the transfer function of impulse input at x of s is equal to a upon s. Now in our question we have been given it is an unit impulse input, so the transfer function so the input in terms of time s domain will be 1 upon s. No, so in case of this impulse input, x of s is straight away a, and in case of this step input we write it as x of s will be a upon s. So in this case the input transfer function, that is x of s, will be 1. So we can write the transfer function of the system as xs is equal to is upon xs kp upon tau s plus 1. Xs we have been given 1, so this will be equal to y of s, and tau and kp we will keep it the same. That is, we can now write y of s is equal to kp upon tau is equal to s plus 1 upon tau, or in other words, you can also write it as Kp upon tau is equal to S minus of 1 upon tau. Now to find this in time domain, so in this given question, we have to find the the response of the first order system in time domain, that is basically in time. So we need to take the inverse Laplace of this term. L inverse of y of s is equal to Kp upon tau S minus of 1 upon tau. So we know that if the, let's say, function in terms of s is given as 1 upon s minus a, then L inverse f of s is written as e raised to at. That is basically f of t is equal to e raised to at. So that is why we changed this equation in form of this 1 upon s minus a, so that we can straight away use and replace these values. So here we can write it as y of t is equal to, this is anyway constant, Kp upon tau, and this we can compare this as 1 upon s minus 1 upon tau with 1 upon s minus a. So from that we can get a is equal to minus 1 upon tau. So using this Laplace inverse formula, we can write this f of t is equal to Kp upon tau into e raised to at, where a is minus 1 upon tau. It will become e raised to minus t upon tau. So the output response for an unit impulse in time domain is given by this term, Kp upon tau into e raised to minus t upon tau. So that is, from the given option, we can select option B as the correct one. So we looked into this question, in which we found out the input impulse response of the first order system for the given parameters. So in the chat box there is a question that how do we determine x of t. So x of t is the input that has been given to the system, and to find the equation corresponding to that, you basically just need to remember each of this equation. So when we say, let's say, ramp input, that means we are constantly increasing the value. So this is my x of t and this is my time, and if you find the equation of this line of this slope a, then the equation of this line will be equal to this at, okay, if it starts at time t equal to 0. So equation of this line is at. So from this plot we get the values of this xt, and then we need to take the Laplace transform to find this a upon s square. Similarly, for step input, this function u of t, that is the unit function, the plot of that u of t is by this is 0 and this is 1. So this function is known as u of t. So from this plot we determine that the x of t will be a times of u of t, where a is the magnitude if it is not 1. Similarly, this delta t is known as Dirac delta function. So you would have studied this in other subjects also, such as this chemical reaction engineering. For this tracer concentration, we just introduced the tracer, and so this is, we are just increasing the temperature for some time, and then again it drops back. So this function is delta t. So that is how we find this x of t, and to find that equation in s domain, that is x of s, we need to take the Laplace transform of each of these terms. Or we can do vice versa. If we know this, then we can take Laplace inverse to find this. That is also possible. So now let's look at another question. So in this question we have been given a plot that is called between f of t and t, and we have been, so basically this is a plot of unit step function, where at time t equal to 3 we are introducing a step change of magnitude 1, and we have to find the Laplace transform of this function. So let's look at the video solution. Hello everyone. The question here we have been given such a plot. This is time f of t. Here we are given a step input. Yes, magnitude 1 at time t equal to 3. So from this plot we can write the function, this step input, as f of t is equal to, so at t less than 0, that is basically on this side, the magnitude of f of t is 0. Okay, so f of t is equal to 0 at t less than 3, and f of t is equal to 1 for t greater than 3. And we have to find the Laplace transform of f of t. So the formula for Laplace transform is given by integration of 0 to infinity e raised to minus of st to the given function f of t dt. So we have been asked to find this right hand side term. So we can write this as Laplace transform of f of t in s domain will become f of s is equal to integration of 0 to infinity minus of st f of t into dt. So the function we have been given is a piecewise continuous function. So basically from 0 to 3, the value of this function was 0 dt, and from 3 to infinity we were given e raised to minus st, the function value was 1 dt. So this is a multiplication by 0, so this entire term will become 0 plus 1, and integration of e raised to minus st from 3 to infinity will become e raised to minus of st upon minus of s. It goes from 3 to infinity. That is, we can write f of s is equal to 0 plus, so if we put this value of time as infinity, so basically e raised to minus infinity will be 1 upon e raised to infinity, so this term will be 0. So 0 minus of e raised to minus s, time we will put it as 3 and minus of s. This will be e raised to minus of 3s upon s. So the Laplace function of the given function, the step input, is given as e raised to minus 3s upon s. So from the given options, we can select the option 1 as our correct answer. I hope the solution to this question is also clear. So basically in this question we were given a function and we had to find the Laplace transform. So the function that was provided was a unit step function, and we had to find, so if we, that is, we were given x of t and we had to find x of s. If you have any doubts, you can write it in chat box, and we will move on to the next question. So the next couple of questions are related to this initial value and final values. So I'll just show what that is. So we are looking into this two theorem, that is initial value theorem and final value theorem. So let's say we are having a response or the output of any system. Let's consider this in time domain. So for first order system, we know that the response will of this dotted line. If we consider a second order system that we will cover, let's say in next class, the response can be such a way oscillating, and the oscillations will be damped oscillations, and it will eventually converge to a fixed point. So over here we are providing this step change. So when we say this initial value theorem, if we want to find the output value at this time instant, that is at t equal to 0, so for that we will be using initial value theorem, and by final value theorem we want to find the final value of this output. The final value will be the steady state value, that is if we have to find the steady state value at this point, we will be using final value theorem. So at this we can straight away calculate that at t equal to 0, whatever the value of, that is at t equal to 0, whatever the value of y of 0, that will be my initial value. Similarly, we can write that at t equal to infinity, whatever the value of the function is, y of infinity, that is my final value. Now to find these values so we will be having the transfer function or the output response in terms of this S domain, that is we will be having y of s, or let's say in general if we have a function f of s and we have to find the initial value and final value based on this f of s, then how do we find it? So for this initial value theorem, the initial value will be given by limit. So in S domain we will write s tends to infinity s f of s, where f of s is the any function whose initial value we have to find. So this is how we will be getting this initial value. Similarly for final value, you can write limit s tends to 0 s into f of s. So let's say we have been given a function f of t. So to find the final value, we will take the Laplace transform of that function, or we will, in most of the cases, we will be providing this function or transfer function f of s, and then we will take the limit s tends to 0, and that will give us final value of that is the steady state value. So this is what we mean by initial value theorem and final value theorem. Based on this, let's look at the next question and it will be more clear. So this is question number 52 of GATE 2021. The question is, a system has a transfer function g of s is equal to 3 e raised to minus 4s upon 12s plus 1. When a step change of magnitude m is given to the system input, the final value of the system output is measured to be 120. So what is the value of m? So in this question we have been already given the final value, and the step change that we are providing to the system is of magnitude m. So the equation will be m upon s, and we have to find the value of this magnitude m. So let's look at the video solution, which will also cover this final value theorem. Hello everyone. We are solving as a transput in the transfer function as g of s is equal to 3 e raised to minus 4s upon 12s plus 1. And then we are giving a step change of magnitude m to this is given to the system input. So input is step change of magnitude m. So basically, let's consider if the system is at this steady state over here, and at this point called t equal to 0, we are giving a step change of magnitude m. So this will be magnitude m. This is x. The output response or the measured system output will can follow this kind of plot based on this transfer function, and we have to find the final value of the output. So whatever this final output is, so that I think we have been given, yes, so that we have been given the final value of the system is measured to be 120. So over here the value is the time, let's consider time taken by the system will be infinity comma 120. So the final value of this output we have been given, it is 120. Over 120 it will become constant, and this step change we have been given of magnitude m. So corresponding to step change we can write this x or the input as m upon s, and in the question we have been asked to find the value of m. So that is, we have been given y of infinity is 120 and m is equal to quotient. Now we know that the transfer function is of the form of ys upon xs. In this question, xs we have been given as m upon s. So that is, we can write y of s is equal to g of s into xs, or m upon s into g of s. And we have been given the value at infinity, that is, we have been given y of infinity and we have been asked to find infinity. Now we have been asked to find the value of m. So we can use the final value theorem for this question. So the final value theorem states that the value of output at time t is equal to infinity, that is y of t, limits t tends to infinity, y of t can be also written as limits s tends to 0, s into y of s. So we will use this final value theorem to find the value of m. That is, limits t tends to infinity, y of t is equal to limit s tends to 0, s y of s. This value is y of infinity and we have been given it as 120, is equal to limit s tends to 0. Y of s was g of s into x of x, and x of s is 1 upon s. So that is basically 3 into e raised to minus of 4s upon 12s plus 1 into m upon s. This s over here, this s will get cancelled out, and then we can replace the value of s as 0 in this equation to find the value as 3 into e raised to minus of 4 into 0 upon 12 into 0 plus 1. So this will be into m. So this will be equal to 3m is equal to 120. So from over here we can find the magnitude of m as 120 upon 3 is equal to 40. So we are giving a step change of magnitude 40, and ultimately the final value of the output is measured to be 120. So from the given options, we have to report the answer in numerical value, so we can write the final answer as 40. If you have any doubt in this question, you can write, and then we can move on to the next question, which is also similar to this one. So in the next question, we have been given a process described by the transfer function gp of s is equal to 10s plus 1 upon 5s plus 1 is forced by a unit step input at time t equal to 0. the output value immediately after the step input, that is at t equal to 0, is dash. So in this question also we have been given g of s, and then we have been given unit step input, and we have been asked to find the output value immediately after the step input, that is at t equal to 0. So since we have been asked to find this initial value, so we will be using initial value theorem to find the desired value. I will play the video solution. Hello everyone, we are solving question 34 of GATE 2022 chemical engineering paper. And the topic is instrumentation and process control. The question is, a process described by the transfer function Gp of s is equal to 10s plus 1 upon 5s plus 1 is forced by a unit step input at time t equal to 0. The output value immediately after the step input, that is at t equal to 0, is dash. In this question we have been given the transfer function Gp of s is equal to 10s plus 1 upon 5s plus 1, and then we are providing the step input, unit step input of magnitude. So if this is our steady state, that at time t equal to 0 we are providing the step input. The magnitude of this input is 1. So this input we can write it as x of s is equal to 1, since the magnitude is 1, and 1 upon s. This will be our input. The output value immediately after the step input. So at this point we have to find what is y. Y is equal to question mark at time t equal to 0. So immediately after time t equal to 0, that we have to find. That is, we have been asked to find y of 0. Now we can use this initial value theorem for this question. So by initial value theorem we can write that the value of the output at time t tends to 0 plus can be also written as limit s tends to infinity s y of s. So we need to find this y of s and replace it over here, then put the value of s as infinity to find the value of y of t, that is the output value. Transfer function you can also write it as g of s is equal to y of s upon x of s, and in this case x of s we have been given as 1 upon s, so this will become x of s to 1 upon s. This is y, that y of s will become g of s. We can put this over here. We get limit s tends to infinity s to g of s upon s, y 0 will be written as limit s tends to infinity g of s, or else we can put the value of s as infinity in this transfer function, that is so we can write it as limit s tends to infinity 10s plus 1 and 5s plus 1. So this we can also rewrite it as limit s tends to infinity. You can bring it out. And like this, we have to put the value of s as infinity. That is, you can write it as 10 plus 1 s. S we are taking 1, 5 plus 1 s. Over here we can put the value of infinity. This with s will get cancelled out. 10 plus 1 upon infinity upon 5 plus 1 upon infinity. So 1 upon infinity will be 0. 10 upon 5 is equal to 2. That is 5 upon 0. So the output value immediately after the step input, that is at time t equal to 0 plus, we can write it as 2. So we can report the final answer as 2. So I hope the solution to this question is also clear. In the earlier question, we were finding the final value and the initial question. In the next question, we are finding the initial value. So until now, we have covered this first order system. And also we have looked onto this final value and initial value theorem. So these theorems are applicable to any order systems. And then we have also looked into these types of inputs. So from the next lecture, we will be covering second order system. So in the first order system, the transfer function was of the form of kp upon tau s plus 1, where the degree of this s or the power is 1s raised to 1. In the second order system, the numerator will be a function of f of s square. So that is why we call it as second order system. So in the next class, we will look into the second order system and various characteristics related to the solution of this second order system. So I guess this much is sufficient for today's class. We can meet on to the next lecture. If you have any doubt related to this first order system, initial value theorem, final value theorem, you can write it in chat box and I'll be here for a while. Okay, so if you don't have any doubts, we can end today's session. Thank you for joining.